everyone. Nikku Madhusudhan. I'm at the Institute of Astronomy at Cambridge. I'm really pleased to be here with you this afternoon to talk about some of the excitements that's happening with JWST, especially on habitable planets and the search for life elsewhere. So, first of all, I would like to thank my collaborators and the community for what a phenomenal development we have made in exoplanet science over the last few decades. And most recently with the JWST, where thousands of people have spent their careers um, working on it and making it happen over the last few decades, right? So we're really grateful to everyone whose efforts have contributed to the present state of the field. So with that, I would like to start off by saying we are entering a really profound time in the history of not just exoplanet science but astronomy as a whole. And the reason for that is that this is the first time in human history that the the search for life, one of the biggest questions that humanity has had for millennia, we have a realistic chance of answering that big question if we are alone. And towards the end of my talk, um, I hope to do justice to that scene, to that state of the field right now. So I'll take you through a journey of what can be done with JWST for different planet types and where actual observations are coming and what is the future looking like. Now, if we zoom out a little bit and ask like the big picture question, is there life elsewhere? Traditionally, our focus has been Earth-like planets, right? So this um, um, sphere that you're seeing on the screen that we call as the Earth, is it a unique sphere in the cosmos? And that is one question that we have asked as a species for thousands of years in various ways. I mean, not just as a planetary phenomenon, not just as asking if Earth-like planets are common, but if actually life is common out there. And that's a question that is on everyone's mind, and it is one of the answering that is one of the key centerpiece of the field of exoplanet science. And answering that question would be the holy grail of the field. But the ground reality we want to ask is, what are the requirements for detecting life on an Earth twin? If we have an exact Earth-like planet elsewhere, how do we detect it and how do we detect life on it? Those are the two uh, questions that tie into the bigger question of whether life on Earth-like planet is rare or common. So, if we want to answer that question right now, it is difficult because currently we don't have a true Earth analog, right? So, we know of thousands of exoplanets today, but we don't know of an exact Earth twin around a sun-like star. The other challenge, of course, is that even if we had an Earth-like planet around a sun-like star, we currently don't have the observational capability to detect a biosignature in the atmosphere of such a planet, right? So then how do we progress from here? If we want to like get this capability to detect a biosignature around an Earth twin, we are still about 15 to 20 years uh, behind schedule, in the sense that on the order of 15 to 20 years would the next observational facilities be possible where we can actually detect a biosignature on an exact Earth-like planet. And this would be done with the likes of the Habitable Worlds Observatory from space and so on. But we also know from just the last 2 decades of discovering exoplanets that exoplanets are extremely common and extremely diverse, right? The statistics are that almost every star would have a planet of some kind around it, and that small planets are extremely common. I like to show this plot. This is an old plot from several years ago, but these planets are from the Kepler mission. But it still drives home this point of statistics that if you just plot all of these planets, just their sizes on the y-axis and orbital periods on the x-axis, you'll see that the majority of these planets are between Earth and Neptune in size, right? So this is known as the sub-Neptune regime, small planets, which form the dominant population, dominant component of the exoplanet population. So just from demographics, we know that small planets are extremely common. And there are also several facilities happening currently and will come. So Kepler has already happened. TESS and CHEOPS are operating and continue to detect small planets, the sub-Neptune planets, or nearby stars, so that the planets are extremely good targets for atmospheric characterization. So the stars being closer means the signal to noise is higher, means you can observe their atmospheres better. And then Plato, which will be coming online soon in the next couple of years, that would would be able to detect Earth-like planets around sun-like stars, around nearby sun-like stars as well. So those also would be good targets for atmospheric characterization. So at least what we know today is that small planets are common and that we can detect them. And the planets that we detect so far, these small planets, are mostly around M dwarf stars, but we can also detect them around nearby sun-like stars with upcoming facilities. So the targets will come online soon. But a bigger question is that, well, what are these small planets like? Because we don't have any analogs of these planets in the solar system. So we have the Earth and we have Neptune in the solar system, but we don't have anything in between. So yes, we have tons of planets in this intermediate range, but we don't know what these planets are like. Are these larger versions of Earth and potentially still habitable with the right irradiation or right equilibrium temperature? Or are they smaller versions of Neptune with thick hydrogen-rich atmospheres, uh, which would have pressures and temperatures at the bottom of the atmospheres too hot to be habitable? Right? So we don't know what these planets are like. So that is one big open question. And that this population is what is also the new frontier in the search for life. In the sense that even though we don't know what these planets are like, even though we have no analog in the solar system, if there is a chance that some of these planets are habitable, then we have lots of targets to look at. Okay. So there is both positive aspects in the search for life if we can find some of these planets which may be habitable, but there are also challenges in that we don't know of the unknown unknowns. We don't know what we don't know even at some point. And the reason, one example of that is that terrestrial planets, for example, have atmospheres that are mostly secondary atmospheres that are dominated by nitrogen, carbon dioxide, oxygen in the case of Earth, and so on. But the ice giants, Neptune and Uranus, are exactly at the other end of the spectrum. They're dominated by H2 rich atmospheres. Okay. So we don't know what the atmospheric compositions of these intermediate planets would be. Would they be more like secondary atmospheres in solar system terrestrial planets, or would they be hydrogen-rich atmospheres? And if they are hydrogen-rich atmospheres, then what kind of life would be possible, if it would be possible, and how thick are these atmospheres, and would they be conducive for habitability? These are all the open questions that we have on this frontier right now. So the targets are there, but we also have a number of like unknowns. So the way to assess whether these are good targets for habitability and search for life is by looking at their atmospheres, obviously. And this we have done very well for giant planets, giant exoplanets over the last more than a decade now. And this is just a summary plot from this review paper, which shows that with different observing techniques and observing frequencies or wavelengths, you can probe different regions of these atmospheres and probe all these various atmospheric processes. We have demonstrated this for hot Jupiters mostly, but giant exoplanets in general, hot Neptunes as well, right? So if you want to understand atmospheric process in the lower atmosphere, for example, you would be looking at infrared spectroscopy, where you could go where the infrared photosphere is much lower than, let's say, the UV photosphere, and then you can probe all these process: atmospheric circulation, vertical mixing, condensation process, clouds and hazes, basically scattering process, and then thermal inversions, how the temperature structures are modulated by the irradiation, and so on. And if you are probing in bluer and bluer wavelengths, by the time you go to UV, you're probing just the very upper layer of the atmosphere where atmospheric escape processes take place, right? So basically, we have um, developed and honed these techniques for atmospheric remote sensing of exoplanets over the past more than a decade now. So we have the techniques to do it. It's just that when you go to smaller planets, the signal to noise gets much worse. So the techniques need to be more and more robust to pick out those signals from very small planets. So I'll just show you a couple of examples of transit spectroscopy. I'm sure many of you have heard about the technique, but just for completeness, this is the technique where the planet goes in front of the star. These are for transiting planets. And as the planet goes in front of the star, some of that starlight passes through the atmosphere of the planet, right? So by subtracting, taking the difference between the spectrum, the stellar spectrum, when the planet is not in transit versus when it is in transit, that differential measurement gives you a handle on the amount of absorption of the starlight that's happening in the atmosphere of the planet. So this is an example with the Hubble Space Telescope more than a decade ago, where we started to get some real good high precision measurements of spectra like this. This is called transmission spectroscopy, where you're just showing the absorption is just the radius ratio squared as a function of wavelength here. So this is a transmission spectrum. So in this case, you can see this bump in the transmission spectrum due to water vapor, and this was for a hot Jupiter HD 209458b. Right? So this is effectively just the transit depth as a function of wavelength. Now, what's happening, what has been happening in the last couple of years is that JWST is revolutionizing this area in a big way. I showed you this spectrum for a hot Jupiter. So for like-to-like comparison, there is also this another spectrum for a hot Jupiter, but with JWST. You can see that in the past, if we wanted to make molecular measurements, it was mostly restricted to water vapor in this narrow wavelength range between 1.1 to 1.7 micron. This was the Hubble Wide Field Camera 3 spectrograph. And that was it. That was the maximum we could go in terms of spectroscopy. But with JWST, it's revolutionizing this area in two directions. One is we are getting very high sensitivity. You can look at the error bars here that are of very high precision. So you can see these molecular features by eye at many sigma. This is the CO2 feature in this hot Jupiter WASP-39b. But also, the wavelength range is much more extended now. Now, in these figures, you're basically seeing from roughly 1 to 5 micron range and numerous spectral features of various molecules. All of that happened within like the first year of JWST operations. The very first observations, one observation of a hot Jupiter WASP-39b in one band is what you're seeing here, okay, with one instrument. So the spectral range has increased, the sensitivity has also increased, and this is the kind of power JWST is bringing to this field, and the lot of promise it's bringing to the field. So with that backdrop of the capability of JWST on one hand, and the availability of a lot of targets in the sub-Neptune regime on the other hand, is what is driving the frontier of the search for habitability and life on exoplanets with JWST. Okay, so in the rest of my talk, I'm going to go through these 5 topics. I'm first going to touch upon concepts of habitabilities. You may be familiar with this, but if not, this would be to complete that. And then I'll be talking about a new paradigm that we're exploring in expanding the range of planets that we can look at. And then we're going to talk about biosignatures and the detectability with JWST. And then we're going to look at a case study with actual JWST observations where molecular features have been detected. And then I'll end with future outlook. So for requirements for habitability, these are all factors that would be obvious to many, but I thought I should put it there for completeness. When one talks about habitability and asks, what are the requirements for a planet to be habitable, these are some of the basic factors one thinks about. You want liquid water on the surface to act as a solvent for a number of these reactions that are essential for life as we know it on Earth. And then you need obviously an energy source. It could be either directly from sunlight or from chemical potentials. And then you need bioessential elements to build the biota, the essential structures that are needed for life and for sustenance. And then these carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur, these are like the top elements that are absolutely essential. And there are several other trace elements that are also required for life as we know it on Earth. And then there are several environmental conditions that you would think about if you want to establish habitability like as on Earth. But even with all that, you can't guarantee that a planet will certainly have life, because there is a whole host of other factors that are also needed for um, establishing whether a planet would be habitable. Uh, in other words, a planet just doesn't sit in isolation. It is a system, it's an ecosystem that's interacting with its environment, both local and the planetary system scale events. Okay, so a planet interacts with the star, with other planets in the system, and then comes the biogeochemical process and geophysical process on the planet itself, right? So this is just to say that when we think of notions of habitability, even though in the rest of my slides I'll go through some simple notions, we always want to have this in the back of our mind that there are a number of factors that make or break the habitability of a given planet. Okay, so we just need to be aware of that. Now, you would have heard of classic notions of the habitable zone. This is just talking about the requirement of liquid water. So the habitable zone is basically defined as the distance from the star, where if you have an Earth-like planet, traditionally this is how it had been thought of, is that if you have an Earth-like planet around a given star, the distance over which that planet can have liquid water on the surface is called the habitable zone. And obviously, as you go to cooler and cooler stars, smaller and cooler stars, the habitable zone goes closer in. And as you go to larger and hotter stars, the habitable zone goes farther out. This is just a schematic to demonstrate the idea, not exact numbers on where the habitable zone sits. Now, these are other calculations of more recent calculations of habitable zone. The original concept was already proposed in like the 90s, and the decades since there have been various calculations for the habitable zone, and this is one of them. And the qualitative features are still the same, but I wanted to show the bottom plot here to say that depending, this was for a roughly Earth-like planet, but depending on what your atmospheric properties are, your habitable zone can actually be different. For example, if you increase the albedo to significantly beyond the Earth's bound albedo, then you could make the habitable zone closer in. That's because you are receiving less starlight um, uh, for the same star. So we want to be mindful when we talk about habitable zones that even within the terrestrial habitable zone, there is a bandwidth over which the habitable zone can be expanded or shrunk depending on what you assume for the specific atmospheric properties of the planet. Okay, but these sorts of concepts give us a general idea of what kind of target we should be looking for, especially for target selection. This is a useful concept to begin with. Now, this is one illustration of such an application. This is the TRAPPIST-1 system you may be familiar with. This is around a very low mass star, about like less than 0.1 solar masses. The star is below this lower edge here, and 4 planets have been discovered in the habitable zone of such a star, and in 7 planets in total. Okay, so this has been over the last several years. This system has been one of our best bets in the search for signatures of habitability with JWST. So there have been a number of theoretical calculations and now observations with JWST which are trying to find atmospheric signals in such planets. But how many of such planets are there? So if we just plot all these planets in terms of their period versus radius, or equilibrium temperatures versus radius, and ask how many planets fit the definition of Earth-like temperatures and Earth radius are smaller, you'll see that there are only a handful of such planets, mostly the TRAPPIST-1 planets, and there are a few more. Okay, which means we are heavily limited by the number of targets if we restrict ourselves just to Earth-like planets. But as I said earlier, we know of a number of sub-Neptunes which are larger than Earth. So we want to ask the question, what are the limits on planet mass, radius, and temperature that are required for habitability, right? So this is where we enter the Hycean paradigm, which was trying to answer, which we came up with while trying to answer that exact question. And this was motivated by this sub-Neptune K218b. This planet has a mass of 9 Earth masses roughly, and about 2.5 Earth radii, and orbits in the classical habitable zone of its host star. The equilibrium temperature is almost Earth-like. The insolation is almost exactly like Earth. So if it were an Earth-like planet with the same Earth mass and radius, we would think of it as a habitable planet. But the slight subtlety was that because of the mass and radius being significantly larger than Earth, we had no analog in the solar system for such a planet, so it wasn't clear if this planet would actually be habitable. In fact, at the time when the planet was discovered, and for a few years after that, the general conception of such a planet was one of a mini Neptune, which is a smaller version of Neptune with a thick hydrogen atmosphere. So you wouldn't have the surface underneath the atmosphere in under habitable conditions. So some of the first HST observations of such planets came around about 5 years ago. And this is a data from one of these works, Beneke et al. 2019, and there was one other study which also found a similar feature. But when we did the atmospheric retrievals with that data set, we, as well as other teams, found that we could explain it with water vapor. So at that time, water vapor was claimed to be causing that feature, but there was significant debate in the field on whether that is actually due to water vapor or methane. For example, if you see these posteriors, the methane upper limit is at 1%. So this is a 2 sigma upper limit. So in principle, you could explain that with methane as well. In fact, that's what this study had suggested, that maybe we are seeing methane. So there was that degeneracy. And then there was one other study which said that maybe it is star spots that we are seeing. So it wasn't clear. But then we used the constraints we had to assess if we can say something about its internal structure. So these are known as mass radius curves. These curves are curves of uniform composition spheres of iron, silicate, pure water, and so on. The density or the mass and radius combination of the planet sat above, so the density was below that of a pure water sphere. Okay, so the radius was a bit larger than what you would expect for a pure water sphere of that mass, which means you need some volatile envelope to explain the planet. So we could come up with 3 compositions that could explain that, just the bulk composition. So a rocky world with a deep hydrogen-rich atmosphere, or a mini Neptune also with a deep hydrogen-rich atmosphere, but now with significant volatile component of like ices, water and methane ices and so on in the interior. And a third possibility was one of a water world with a thin hydrogen-rich atmosphere. Now, the interesting bit was that for that, if you ask what is the temperature and pressure at the boundary between the atmosphere and the interior, obviously, because of the degeneracy in those three solutions I talked about, there is a wide range of temperatures and pressures that are possible. And most of those would not allow for habitable conditions. They would be too hot for liquid water. In fact, most of them would be in supercritical state. However, they did allow for a small number of solutions that allowed for liquid water. Okay. So, in principle, there was the possibility of a liquid water ocean under the H2 rich atmosphere. These are showing some temperature structures for different assumptions of the haze strength that could allow for a liquid water ocean underneath the atmosphere. So this is what motivated us to propose this new class of planets. The basic question is, well, if K218b, there is some possibility of liquid water underneath the atmosphere, what other planets are out there that could also be like that? And then we came up with this range in masses and radii. This cyan region here is what would allow such conditions for temperatures below about 400 Kelvin equilibrium temperatures. So we saw the classical habitable zone that looked like that, but if you now try to derive the hycean habitable zone from such calculations as I described in the last slide, you would find that the habitable zone would be much wider compared to the terrestrial habitable zone. Okay. And that is what motivated us to look if there are any other targets beyond K218b that fit these descriptions, and we could come up with about a dozen planets that allow for such conditions, Hycean type conditions. But then how do we confirm a Hycean world? And that's when we'll have to look into their atmospheric observations. So this is just an artist's rendition of what a Hycean world would look like. It would have a hydrogen-rich atmosphere at the top with hazes potentially, and then a ocean-covered surfaces. Now let's look at detectability. So what I'll do here is I'll go through a big picture assessment of what is a biosignature and what kind of biosignatures are we after, and whether we can detect them with JWST. So again, if we take a step back and think about Earth, well, how do we establish that the Earth is actually hosting life? We would look for atmospheric features in the spectrum of the Earth, and then you'd come up with these conditions that such a signal should qualify for it to be a biosignature gas. So it shouldn't exist naturally in ambient conditions, for example, in chemical equilibrium at a given pressure and temperature, but it should also not be produced by any other means naturally, like geochemical processes or photochemical processes. And then, even if it's robust to those two conditions, you need that molecule to be produced in enough quantities for it to be observable, right? Enough concentration. Finally, you could produce a lot of a biosignature, a biotic molecule, biogenic molecule, but it also have to have a strong spectral signature that you can observe, right? So if you think about what are those molecules on Earth that fit all these characteristics, then you'd come up with oxygen, ozone, nitrous oxide, and to some extent methane. However, there are a number of other biomarkers on Earth. So besides these prominent biomarkers, there are a number of other molecules that act as good biomarkers that are unique products of life on Earth, but are produced in very small quantities. And here we are talking about molecules like dimethyl sulfide, methyl chloride, mercaptan, methyl mercaptan, and so on, which are actually very good indicators of life. It's just that on Earth, DMS, for example, is produced at generally less than a part per billion, which means you wouldn't see it if you look at an Earth-like planet. The signal would be too slow, too low. However, because I mentioned about these Hycean worlds with their hydrogen-rich atmospheres, the notion of the hydrogen-rich, the notion of having such a hydrogen-rich atmosphere means that these planets would also be very good for atmospheric detectability, because your scale height is higher, which means your atmosphere is more puffed up, so your signal in transmission spectroscopy will be higher. Okay, so suddenly these secondary biomarkers on Earth, which are in small quantities, can be detectable, more detectable in these planets with hydrogen-rich atmospheres than they would be on rocky planets. And if you ask where are the molecular contributions in spectral space from all these molecules, they're as expected, all in the infrared. But the reason I'm showing you this plot is because before JWST, as you saw, we were restricted to largely below 2 micron, especially like 1.7, 1.8 micron. Even though the sensitivity was still low with HST, we didn't even have the capability to look in the mid infrared, where a number of these biomarkers have very strong opacities. And this is what JWST is bringing to the field, is that this extensive wavelength coverage means that all of these molecules are now potentially observable if they're present in large enough quantities. Okay. So now let's look at what can we actually do with JWST. So I showed you this slide with JWST observations of a hot Jupiter. But if we do that exercise, if we ask, well, what can we detect in TRAPPIST-1, for example, if it had ozone, can we detect it? The answer is yes, but only with tens of transits with JWST. So we are talking about hundreds of hours of JWST time investment. And if we do that, we can in principle detect ozone in some of these planets. On the other hand, we could detect other molecules like carbon dioxide, methane, and so on with lesser number of transits with JWST. So those kinds of observations are already happening right now. But there is this one observation of TRAPPIST-1b that was reported. This is not a habitable planet, but still as a proof of concept, a spectrum was reported, and there was no detection per se. But so you see these data points with error bars as actual JWST data in black. And you can see that the spectrum is mostly flat, but even when there are features, uh, we think as a field, we think that that is contributed by significant stellar activity of their host stars, because the star is a late M dwarf, so it is very active. So what we are learning for characterization of rocky planets, especially rocky habitable planets with JWST, is that the challenges are twofold. One is that their atmospheric features are inherently much harder to detect, but there is also stellar contamination, which is a key challenge for atmospheric characterization of such planets if they orbit late M dwarfs, which are very active. Okay, this is another case of another planet also in the habitable zone. This is LHS 1140. So the planet is shown on this mass radius curve here, around 6 Earth masses and around 1.7 Earth radii in size. Again, you can see some seemingly prominent feature here, but we think in the field that it's due to stellar contamination. So what we are realizing more and more is that for when you look at planets orbiting late M dwarfs, that stellar activity is a significant challenge. So there are a number of observations that have been scheduled with JWST that are happening right now, and some already happened, where we are looking, as in the field, looking to characterize these small planets with a lot of JWST time investment to see if we can tease out any such signals. And then we come to these hycean candidates I was talking about earlier, where the surfaces would be ocean covered, atmospheres would be hydrogen rich. And that combination means that for any given mass, this is the largest size habitable planet that you can think of. Okay. And when that happens, your transit signal is much better. And as an example, for a number of these hycean candidates, we calculated, these are simulated observations, we calculated a few years ago that you need only a few tenths of hours to be able to detect molecular features in such atmospheres. So we decided to test this out for a planet K2-18b, and just before JWST was launched, we had proposed to look at this planet based on the previous HST studies and the debate going around the interpretation of those observations. We proposed that we would look at this planet again, and we were successful. We were granted time to look at this planet, and our key goal was to study chemical disequilibrium in the atmosphere of the planet. Okay, what does that mean? That means that if the planet is habitable, if it actually has a surface underneath, that would disturb the equilibrium state of the atmosphere, and you should see some evidence for that. In chemical equilibrium, we expect prominent molecules like water vapor, methane, ammonia to be dominant, especially if you have a deep hydrogen-rich atmosphere like a mini Neptune. But if it's not in chemical equilibrium, it has an ocean under a shallow atmosphere, then that would disturb this equilibrium. So we observed, we were granted time to look at 3 transits in 3 different instruments, JWST NIRSPEC, NIRIS, and MIRI. And so far, only 2 of these observations have been published, which I'm going to go through now. And I'll spare all these details, but basically the data was very good. You see this white light curve in the NIRSPEC observation between 3 to 5, roughly 3 to 5 micron. And this is, if we now combine all those observations from the NIRSPEC and NIRIS data sets, let's see what the spectrum looks like. So I showed you this spectrum with HST before, which was obtained with over 50 hours of HST time. And with just 2 transits with JWST, that's about 14 hours of JWST time, we got a spectrum like that. Okay, so you can see like the remarkable difference between the 2 spectra. Now, this confusion that we had, whether this was due to water or methane, completely went away with just the very first observations. Okay, so number of these peaks that you see are all due to methane, and we know that now very clearly. There is also this other peak that is due to carbon dioxide, and then we think there is some hint of DMS here, but that wasn't a very significant detection. It was of low statistical significance. So we should just take a step back and just realize that the fundamental advancement that has been possible with JWST in just obtaining this spectrum. This was the first time ever that carbon-based molecules have been detected in a habitable zone exoplanet. Okay, and that's just with 14 hours of JWST time. This is a plot showing all the contributions from the different molecules to show how you can see these multiple methane peaks are embedded in this data. Okay, so all the points with error bars are the data, the curves are all model fits to the data. Okay, now the reason DMS was such a low signal and we could not detect it very clearly is because of this degeneracy between the DMS feature and the methane feature within the same band. Similarly, DMS also has degeneracy with CO2 in this band. You see the overlapping features. So it's very hard to disentangle, to break those degeneracy with current data. So then we took those data and did atmospheric retrievals on it. What is an atmospheric retrieval? It's basically fitting an atmospheric model with the spectrum that we observe using some parameter estimation scheme. In this case, it was nested sampling that we used with a software called MultiNest. And the atmospheric models has the temperature, structure, and composition as free parameters, which means from this parameter estimation, you can extract the posterior distributions of all those free parameters and make statistically sound estimates of both their presence and their abundances and so on. So these are what the posteriors look like, the probability distributions of each of the molecules. And you can see methane is estimated very precisely with error bars less than a dec, less than 1 dex. And same for CO2 roughly. So both of them are present in very high quantities, about 1% each, but DMS was not retrieved very precisely. Now, it depends, the precision on the DMS measurement depends on what offset you use between the detectors, and depending on those assumptions, your signal can be diluted significantly. Okay, so we can discuss this more if people have questions, but the summary is that these 2 detections were pretty secure, but this wasn't. On the other hand, we did not detect water anymore. We did not detect ammonia or any other species. Now, why are these species important? What does this mean? The very detection of an H2-rich atmosphere with high abundances of methane and CO2 and non-detections of these species like ammonia and CO basically are consistent with what was predicted for a Hycean world. Okay, because the ocean, presence of an ocean, absorbs some of that ammonia. Now, this DMS I mentioned, this marginal evidence, why is that important? It's important because it was predicted as a robust biomarker for Earth-like planets as well as hydrogen-rich atmospheres, including Hycean worlds. Okay, and the non-detection of H2O is also consistent with the evidence for clouds and hazes that we found in this planet and the low stratospheric temperatures that were retrieved. So, in summary, all of everything that we detected with those observations so far for K218, we are consistent with a shallow or a thin H2 rich atmosphere and an ocean surface, which is incredible if you think about it, because even a few years ago, no one would have guessed that this would be possible with JWST. And more importantly, all the inferences that we're making with the observations today have been predicted before the observations were taken. So there was this prediction that if you have a deep atmosphere, you should see plenty of ammonia and CO along with other species. But if you have a solid surface, then you wouldn't see a lot of ammonia in the atmosphere. Okay, but if you have an ocean surface, it'll decrease even more. Okay, so that was our conclusion from that study, that with those observations we could already potentially establish that this planet is indeed an ocean world with a hydrogen-rich atmosphere. So that opens a new regime in planetary habitability that is actually observable with JWST. Okay? So where do we go from here? So there have been studies in the field on how do you establish a biosignature. So there are several questions you want to ask in terms of standards of evidence. You want to ask, well, is the signal actually authentic? Is it adequately identified to be from the molecule you are associating with? Those are just observability questions or detection questions. And then you want to ask questions about the interpretation of that detection. So currently, obviously, with DMS, which was predicted to be a biomarker, it doesn't satisfy this first criteria because, as I said, the signal wasn't of much robustness at all, right? Um, but then there are also other questions we want to ask about the interpretation. If the signal is true, whether there are other sources that are abiotic that could also produce such a molecule. And are there independent lines of evidence? Is there another instrument with another observation that you could use to also detect the same species? And that would make it a bit more robust. So there are many open questions, obviously, along these lines, not just about biosignatures, but also about habitability itself. For example, is the liquid ocean actually possible? What is the albedo of the planet? What is the temperature structure? All of these are open questions that I won't go into. But this is just to say that these observations are already opening a number of questions that are essential to establish essential to answer in order to establish the environmental conditions and the potential habitability of such planets. I will just, in the last couple of minutes, I'll just touch upon two questions. For example, you could ask, well, if you have an ocean world, a Hycean world, how deep would the ocean be? This is just to put in scale, like how strange these planets would be relative to Earth. So if you have such a planet, you see Earth's maximum ocean depth is about 10 kilometers, which is marked here, and that is just the atmosphere. But if you have a Hycean world, the depth of the ocean could be hundreds of kilometers. And even then, you may not reach actually the rocky ocean floor or this a silicate rich ocean floor. You would reach high pressure ice below the ocean floor, which continues being high pressure ice until the very like core, which is consistent, which would consist of rock. Okay, so that's a very different sort of planet from what we are used to on Earth, even from a habitability point of view. Naturally, that raises questions on whether, well, you may have an actual Hycean world, but is life actually possible without access to these minerals that interactions with rock gives you on Earth? And then we did other studies a few years ago to establish, to understand if actually that is possible. And we very quickly established that that is not an issue, because you can bring the bioessential elements through multiple other sources into the ocean. Although, this is not entirely a solved problem, we need to do like more detailed studies to see how each of these factors, exactly how much they can contribute. But the zeroth order studies at this point all point to these planets being promising places to look for habitability and life. So then the last question is, well, did we just get lucky with K28nb, or there are other targets out there that are also promising? And just as of last year, there was this planet TOI 270d, and you can look at the two spectra and how similar they are. Okay, so the inference for this planet was also that it had methane, and it had also carbon dioxide had been inferred. We did not infer DMS significantly at the time, but we did find a carbon disulfide, which was another biomarker that is predicted based on previous models, but that I suppose one can also get that by atmospheric chemistry, and that has not been robustly established just yet. So to conclude, what we are seeing essentially in the field right now is that we are taking small steps in redefining and expanding the definition of habitability itself beyond just focusing on Earth-like planets. Because nature has offered us this wide range of environments, and it is up to us to see which of these could be conducive for habitability and life. And the only way to know for now is to do all these theoretical studies and expand our horizon and establish which of these could be potentially habitable, at least theoretically. And then this new revolution that's happening in the field is the advent of big telescopes, especially with JWST, which is now demonstrating that actually, if the atmospheres are hydrogen rich and potentially habitable, and those are the kinds of planets that are actually accessible with JWST. So that's where we are looking at right now. And very soon, the extremely large telescopes on ground will also start. The 40-meter class telescope in Chile will start by ESO, and we should be able to detect atmospheric features of some of these planets with that as well. So this decade, in my view, would serve as the launch pad in the search for life. When we'll detect a robust biosignature is an open question at this point. That's because even if we detect some of these molecules, we still need to make multiple observations to establish those criteria that I mentioned earlier. We want to establish that the signal is robust and that it can be robustly associated with life. But nevertheless, our facilities are already launching a new era in the search for life elsewhere. So in my mind right now is that we are entering this area where we can finally ask um, uh, if we are alone in the universe, and we might be able to answer that. But more generally, any detection of a biomarker will take us towards assessing life as a universal process across multiple different environments and not just Earth-like planets. Thank you.